loco. That's what they are. Just so they can lose to my Skyline Eagles. You're just going to sit there and take it. You're not going to fight back?
No, you'll just swim faster.
All right. Where did we end yesterday? Perfect. Where did we end? Next slide.
This is the first slide we're on, actually.
Oh, this is it?
Well, actually, maybe the one before, oxidation reduction, the one with the diagram, but other than that.
Boom, right here?
Yeah.
Okay, this is kind of weird. When it goes full screen, it doesn't fit full screen. If I go partial screen, it fits. I don't know. America. That's always the answer to everything. All right, let's talk. Today, we're going to talk some complicated stuff. And then we're going to give you an assignment that most of you will feel like I didn't even explain how to do. What's the answer? America. So we're just fine. All right? All in favor? Say me. Me. All right. I know it's annoying when I sit back here, but I forgot to record. This is how I teach in first hour all the time, because I record and then I put it on the internet for no one to watch. Almost all my class lectures have under 2 views. And I know one of them's me because I have to double check it works. And the other one was probably also me. Like, hey, you look good, Tom. All right, actually I don't. Hello. Oh, that's a lot of them. There you go, my friend. All right, here we go. Oxidation-reduction reactions. An electron moves from one place to another. Good enough? I think we were talking about that yesterday. To determine if an oxidation-reduction reaction has occurred, we assign an oxidation number to each element in a neutral compound or charged entity. Okay, first off, if a lone element is present, then you have a redox reaction. So one thing, you can just simply look and identify most redox reactions if there's a lone element on either side of the arrow. Now, it's really nice when there's a single element on both sides of the arrow, because then it's a piece of cake. But anyway, if you see a lone element, then it's a redox reaction. So what I mean by that is when you have like copper plus silver nitrate goes to copper 2 nitrate plus silver, you have a lone element right there. That means oxidation and reduction, or a redox reaction happens. You have a lone element right there. If it's on both sides, it's super easy. But you don't always have it on both sides. This could also be an oxidation-reduction reaction, just a simple decomposition of potassium chlorate. It will decompose into calcium chloride plus oxygen. I have a lone element right there. That means this is a redox reaction. And it's a little bit complicated, but we'll come back to that eventually, and we'll work through it. You'll think, oh, I can do this. All right. So what we need to do for oxidation-reduction reactions, which I'm going to for now call redox reactions from now on, because oxidation and reduction reactions is just too hard to say. All right. So first thing is you need to assign their oxidation numbers. So there's a bunch of rules that we're going to tell you that you need to know. Now really, if you just know 4 of them, you're going to be fine. But the first rule is if you have an element in its elemental form, its oxidation number is 0. Yep. So like chlorine is elementally found as Cl2. All right. If it was Cl1, it'd be all sorts of nasty, and we wouldn't be happy. Okay. So first off, piece of cake. If it's a lone element, it's a 0. Next, the oxidation number of a monatomic ion is the same as its charge. So let's use a simple reaction here. Sodium plus chlorine goes to sodium chloride. we can use just these two rules to assign oxidation numbers. Sodium is an element. Chlorine is an element. Sodium, since it's a monatomic ion, its charge is its oxidation number. So it's in family 1 plus 1. Chlorine is a monatomic ion with a charge of minus 1. Now, oxidation has occurred because we had neutral things and they are now charged.
But they are monatomic, right? Because they're stuck together.
But they're ions. They are made out of ions, and they are monatomic because there's not more than one.
Because they're not technically bonded, really. They're just attracted.
They are attracted, but we do call it an ionic bond. Next. Nonmetals tend to have negative oxidation numbers. And just because life's awesome, just be aware that although some are positive in certain compounds or ions, that's a life wrecker right there. Okay? That would be like saying you always stop for a red light unless it is. And you're like, I got this thing. But you're like, wait, is this one of those times where I don't have to? All right. Oxygen. This is one of our main ones. Oxygen has an oxidation number of minus 2. Always except in peroxide, in which it has an oxidation number of minus 2. We hardly ever deal with peroxide, so memorize oxygen's a minus 2. We're going to use oxygen to determine a lot of other things in this game, so you have to know oxygen's a minus 2. Now, hydrogen, this bugs me. It is a minus 1 when bonded to a metal, but we hardly ever deal with that. So I want you to realize hydrogen is a plus 1 99.9% of the time. In this class, we hardly ever, if ever, deal with metallic hydrides. We deal with things like acids or ammonia. Okay, these are huge. This one, this one, this one, and one coming up. Non-metals tend to have negative, blah, 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 whatever. Fluorine always had an oxidation of minus 1. That's fine. The other halogens, yada, yada, yada. I wouldn't write any of these down. Here we go. The sum of oxidations is 0. That's like the number one thing. The sum of the oxidation numbers in a neutral compound is 0. The sum of oxidation numbers in a polyatomic ion is the charge of the ion. Now, the reason we didn't write down the last slide is because every other rule will just prove that other page anyway. Okay, so the 4 big rules to finding oxidation numbers is first, element equals 0. Okay, second, total equals 0. Third, oxygen equals a minus 2. Last, hydrogen equals a plus 1. You can do almost, if not all, problems just with those 4 and using these 4 to generate the others. Now, in tons of ionic things, the oxidation number and the charge are just exactly the same thing. So there's not, are you okay? Okay, there's not a lot of brain power invested, but for some things it gets really tricky. So let's see what this slide offers me. We're going to come back to that in a second. Let's just practice one here. So if I have magnesium nitrate, and we could do all this stuff. But what I want to do, I want to find the oxidation number of every element involved in magnesium nitrate. So it's Mg, it's N, and it's O. So what we would do is we would use our rules. Is there a single element? I don't like how I boxed those. Is any of this alone? No. All right, so I don't need to worry about that. I'm going to say that I know the total equals 0. And then I am just going to go with what I know. All right, in an ionic compound, a monatomic ion just has the same oxidation as its charge. So magnesium plus 2. All right, then I'm actually going to come down here just for explaining sake. And I'm going to do it for the NO3 minus all by itself. NO3 minus. So we have an N and 3 O's, and its total charge equals -1. Are you okay with that? I'm going to put a 1 right here. So I will use my rule for oxygen. Oxygen always has an oxidation number of what? -2. And then I have to find nitrogen based on my oxygen. So please follow this logic. The total charge is equal to -1. Oxygen's a -2, but there's 3 of them. So what's the total amount of charge oxygen is giving? It's a -6. So I have this little thing right here. Something -6 equals -1. What is that number? It's a +5. You with me? So the oxidation number of nitrogen in this compound is a +5. Oxygen's oxidation number, what is it? It's not -6. It is a -2. Okay? What is going on here? Somehow, look at this. All it's showing in the video screen is right here. I'm lost. Hold on. There we go. All right. Did that make sense to anyone? Raise your hands if that made sense. Okay, let's do this slide then. What is the oxidation number of the red atom in each of the following? So it's nitrogen in all of them. What is its oxidation number? Okay, try all 3 of these. All right. Now, this is a new concept, so I know it's a little bit tricky. But really, when this clicks, this is one of the easier things that we ever do. Now, don't have a heart attack. I doubt it's clicked yet. NH3. All right. We're just finding the oxidation number in each of them. There we go. So, N doesn't have a specific rule, but hydrogen does. What's hydrogen's specific rule? It's a what? It's a +1. Now, it is a +1, but we're going to use the fact that there's 3 of them to find N. All right, and you're going to think, well, Davidson, this is easy. This is just the drop and swap in reverse, but it's not that easy, even though it works out. So 3 +1s mean the total charge, not the oxidation number, just the total charge that H equals is +3. So N, it's something +3 equals 0, so N has to be a -3. Who had that answer that N was a -3? Raise them high. All right, good. Feels good to have a right answer once in a while, right? Nothing beats that. All right, NO3 minus. We just did it, but we'll walk through it again. NO3 equals a -1. N isn't special enough to have its own rules, but O is. O is a -2. but there's 3 of them, so 3 times that is a negative 6. Something minus 6 equals negative 1 plus 5. Raise your hands if you had it right. Everyone should have had that because we did it 30 seconds before I asked you to do it, right? All right, is this N2O4?
Yeah.
All right. N2O4. Once again, nitrogen not cool. What does this add to? 0. All right, oxygen, always a minus 2. There's 4 of them, so its total charge is negative 8, right? All right, now, just be careful of this. Something minus 8 equals 0. What is that something? It's plus 8, but there was 2 of these, so N has to itself be a plus 4. So plus 4, plus 5, minus 3, all on the same element. That just doesn't seem fair. But let's remember, it's America. We have the right to do whatever we want. Good? Who had them all right? Raise your hands. Well, heck, you don't need me. You don't need me at all. Which is great. I will sit here and relax and make you do more work. Sound fun? Oh, dang. Okay. All right. There's that from last hour. All right, here we are. Now we're going to talk about a true redox reaction. All right. So first thing is what we just taught you. That's how to find oxidation numbers. But now we're going to use them in a reaction to account for what really happens. All right. So someone pick your favorite element from family 1.
K.
Oh, I heard 2 Ks and 1 sodium, so we'll go with K. All right. I have potassium. Plus, I'm going to add it to copper to sulfate. Is this a redox reaction?
It's not if you want to.
You're right. I did that on purpose to make it easier, and then I was dumb. Thank you. All right. So, is this a redox reaction? Yes. How do I know? All right. There's your huge red flag. Lone element, life's going to suck. All right. Now, when this reaction happens, it's a single replacement reaction, right? I have K2SO4 plus Cu. All right, now, remember I said if there's a lone element on both sides, life is dandy. This is when it gets the easiest. So I'm going to assign oxidation numbers. 2 of them, I don't even have to think, a 0 and a 0. Right? That was nice. All right, then I'll just keep moving left to right. What is copper here? I said it out loud. It's a 2, copper 2 sulfate. And then do yourself a favor. Is SO4 exactly the same on both sides? Yes. So is anything going to change? No. So don't waste your time. All right, so come over here. What's the charge of K? Plus 1. All right. So now, what I have to do is I have to identify what has changed in my redox reaction. So here we go. I do the following. I need to get rid of these blue arrows. Hold on. Okay, this is the custom of how to do redox reactions. You put a bracket from one thing that changed, or well, I don't know, from the same thing to the other thing, identifying that it is changing. Then I'm going to put another bracket from copper over to the other copper, and that identifies the 2 things that have changed. You with me? Okay, time out. I'm going to say something here. Leo, the lion, says grr. Okay, seems dumb. I would write it down. Leo the lion says grr. This is your oxidation thing to remember. Leo stands for lose electrons, oxidized. GER stands for gain electrons reduced. It's just something to help you hopefully memorize something. So here we go. Well, do you need it up there still?
What does the second one say?
Well, it looks terrible. Gain, G-A-I-N, electrons reduced. Now, remember the very first slide that we showed forever ago yesterday, it said that you could, or that you have to have oxidation and reduction. You can't have one without the other. So let's come back here. All right, what we identify is who lost and who gained. So a 0 going to a +1, is that losing or gaining? It's losing. You win. Because what are we gaining and losing? A negative thing. And that's one of the things that I'm sure Satan invented. He's like, let's make the electron negative so you can gain and become negative and lose and become positive. And that will screw kids' lives over forever. All right, so here we go. It went from a 0 to a +1. So you're going to write lost, and how many electrons? 1 electrons. And if it lost an electron, it was oxidized. You can just put an OX. So that's how we identify it. We bracket it and then label what happens. So copper had a +2 to a 0, which meant it gained. And it gained what? 2 electrons. And if it gained, it was reduced. Now, something is extremely wrong right here. What's wrong? It's not balanced. You can't lose 1 and something gain 2 unless you're on a diet. That happens a lot. Okay. I never balanced the reaction, right? So there's a 2 right here. So I have to put a 2 right there. Everything else is a 1, right? Now, be careful how you account for this. You don't just change this number to a 2, because that would be a lie. Did the potassium lose 2 electrons? No. You'd go like this. That implies that something lost 1 electron twice, which is the true way to say it, is it not? You didn't like that, Clark?
No, it sounds like I understand what you're meaning, but it still sounds
What did I say wrong?
Yeah, you said one thing lost something twice, but it's 2 things lost something.
That's what I meant. Okay. So for the record, I meant to say that this thing lost 1 2 times. All right? Did I say it wrong again?
Yeah. Lost one thing once.
Whatever. On video, I don't know. I'm clearly an idiot. That's what I'm trying to say, whether I'm saying it or not. All right. Was that tons of fun? Good. Here we go. Okay, try and do this same thing with this for the next couple of minutes. All right. So first thing, identify oxidation numbers. On this one, it's not very hard because we do have a lone element on both sides. If you have a lone element on both sides, that identifies already what will be oxidized and reduced. You don't need to worry about these things. So you have a 0. A 0. This is iron what, nitrate? Good, +3. That's because of this number right here. Magnesium is always a +2. So I'll bracket my magnesium. I'll bracket my iron. And then if I go from a 0 to a +2, what happened to me? I lost 2 electrons, which meant I was oxidized. All right, iron 3 to 0, so what happened? I gained 3 electrons, and I was reduced. Whoops, this can't happen, so I have to make them equal each other, which will all be great when I balance this out. If I have a 3 and 2, I should use the swaparoo. So 3, 2, 2, 3. So I take this coefficient right here, I put it in front of the 2. I take this coefficient here and put it in front of the 3. And now I have a 6 being lost, and so +6 and 6 being gained, and that adds to 0. Who had that exactly right? Raise your hands. Okay. Let's go back forever and do one more before we do something else.
So the oxidation or reduction numbers of the entire reaction will equal 0?
The total change of electrons will always equal 0. All right, let's get this out of the way. This might take a lot longer than it's worth. All right, now we've done easy ones. Let's do one that's a little bit harder. First off, let's see. Oh well, we'll leave it there. So I only have one lone element, and it's oxygen. So I'm going to put a 0 there. All right? Everything else, it's going to be some work to do. First off, this one's easy. Potassium's a monatomic ion, and its charge is a +1. Chloride, monatomic ion, and its charge is -1. Okay, we could have just found that in its families, but that was easy, right? Potassium over here is still a monatomic ion, so it is +1. That means potassium has nothing to do with this redox reaction. So then I got to get to ClO3. Remember, all of this up here is going to add to 0. The oxidation number of oxygen is always a -2, unless it's a lone element, right? All right, so I have total charge. I have 3 times -2 is what? -6. So I have +1 something, -6 equals 0, and this will be our good friend we've used before. It is a +5. All right? You okay with how I did that? Well, there is. That erased itself. Just remember, that's the oxidation number, though, not that.
So it's because of the +1 over there.
Yep, +1 +5 -6 equals 0. All right, so now I identify who has changed. Chlorine had one heck of a change, right? And oxygen had a change. So chlorine +5 to a -1. What happened to it? It gained 6 electrons, which means it was reduced. All right. Then oxygen -2 to 0. What happened to it? It lost 2 electrons, which means it was oxidized. Which is ironic because oxidation was originally just meaning that oxygen was in the reaction. All right, now this doesn't work, right? So we better balance. I have a 2, 3 again. I'm going to put a 3 here, a 2 here, and a 2 here. All right. So this is a teeny bit tricky. How many oxygens are here? Right here? 3, but there's 2 of everything, so there's really 6. So really, 6 oxygens lost 2 electrons for each one. Then, down here, how many total chlorines did we have? 2. So 2 chlorines gain 6 electrons each. So what's the total change here? 12 minus 12. That equals 0. So I have correctly balanced this, and life is bueno. All right? Thank you, Fred.
Yeah.
Hudson, you are out of here. All right. Are we okay with this? It's not the easiest thing we do, but it's not the hardest either. All right, let's skip all the way to some actual notes again from the PowerPoint. All right, a displacement reaction. This is annoying. This picture's not even very good anyway, so let's make it smaller. In displacement reactions, ions oxidize an element. The ions are then reduced. This is a redox reaction. Every single one of these that we just did, except for the last one, was a displacement reaction. And we've already learned about these. We call them single, replacement reactions. Okay? The only difference is a displacement reaction always involves a metal in a solution. Some single replacements don't have a metal in a solution, but it's okay. All right? So, all we do, we add a metal to a solution and then see what happens. All right? So here's our example. We have copper plus silver. Now, notice this is Ag+. All right? The Ag+ came from AgNO3. How come they didn't bother to write the NO3 on either side? Because it's the same. So it's a spectator ion. Okay? So this would be your net ionic reaction. It's also a displacement reaction. And just to make your life horrible, it's also a redox reaction. Okay? It represents everything. So I take elemental copper, I add silver nitrate, and the silver comes out as a solid and starts to plate onto the copper wire. As time goes on, you're left with a hollow tube that looks springy, but it would just crumble immediately, of silver and a blue solution. Why is the solution blue? All right, anything that has a copper ion in it will be a blue solution. Okay? I don't know, we all right with this? It's a redox because we had a lone element and a lone element. This became +2, so it was oxidized. This went from plus to 0, so it was reduced. All right. The reverse reaction, however, does not occur. We can't get it to go the other way, and it's because of this thing right here, the activity series. Add this to your notes, Christine. Any metal on the list can be oxidized by the ions of elements listed below it. So I added that, Christine. This is in your reading. And what it's trying to tell you is very simple. Let me shrink this a little. So any metal, and what we mean by that is just the element on the list can be oxidized by the ions of elements below it. So the ions. So this is just what was said. So we had copper plus silver nitrate went to copper 2 nitrate plus silver. This reaction happens because it follows this rule. Any metal, that's the copper, on the list can be oxidized by the ions, that's your Ag plus right here, listed below it. So you would look. To know if this happened, you would find your ion, and it's right here. And as long as the metal is above it, which copper is, then the reaction does go forward. The reverse would not be true. Okay, so let's think about this. We did some. Let's go back real quick. Forever. There is one. So magnesium plus iron nitrate. What's my metal? The magnesium. So to see if I was right and this reaction really happens, magnesium's the metal, the ion is iron. So Fe plus 3 must be lower than Mg for this to really happen. So let's check our list. All right, let me get rid of this. So I see magnesium right here. That's my metal. My iron is right here. This is my ion. So is my ion lower than my metal? Check mark. Yes, that was written correctly. All right. The first one we did was potassium plus, was it copper sulfate, copper 2 sulfate? It was. So let's check. My metal, all right, my metal is right here. I'll put it in red. My metal's right there. My ion is copper, which is right here. In this red example, is my ion lower than my metal? Yes, it is. So this reaction does happen. Now, if you remember when I asked, I said, tell me your favorite family 1 metal. And you told me that, and then I reacted it with copper 2 sulfate. That's because anyone that teaches chemistry knows that anything in family 1 is really high. Okay? Anything in family 1 is very, very easily oxidized, meaning they're super reactive. Okay? All right. Now, the rest of the hour, I'm going to pass out a worksheet that is hard. Okay? We're going to have you work through it in groups, and we'll continue working on it tomorrow. So it says, balance and identify the type of reactions for each of the following reactions. For precipitate and acid reactions, give the net ionic reactions. For redox reactions, identify the elements oxidized and reduced using brackets. It's fun. You write on this. So dry skin today. All right.
Okay, so redox reactions are always forming ionic bonds, right? Because you wouldn't ever have them losing an electron unless
Not necessarily. Seems like it, but not. No.
Okay, great.
Sorry.
That's all right. Thought I had something right.
Yeah. Yep, it is. So if you have that. So if you're watching on film, these are the first 4. Pause it. No.
Vaudeville runs into a kicker at least once a game, so I'm going to pull out my inner soccer player this week.
So you're going to what? Oh, pull out your inner soccer player.
Well, it's going to be good.
Okay, the rest of the hour we would just be working on these.